we talked about last time, we talked about units. We have our SI units. These are things like kilograms, meters, seconds, right? And the SI units were what? What is an SI unit?
Standardized.
Yeah, it's a standardized unit, right? So it's a standardized unit. Unit used by all natural sciences, right? And then from the SI unit, we could have our derived units. Does anyone remember what the derived units were? We didn't talk a whole lot about them, but these are more common units that you'll see. What a derived unit was?
Like a combination.
It's any combination of our standardized unit, right? Like a volume is a derived unit because it's a length cubed, right? So combination of standardized units, right? So example, volume, which is a length cubed plus u. Or another one that you guys measured would be like density. Does anyone remember what the units for density were? Yeah, it's the mass, right? So it's a mass divided by a volume, right? So it's a mass over a volume. In the standard one you'll see for density is grams per centimeter cubed, or sometimes centimeter cubed is abbreviated as a cc. Right? Milliliter, centimeter cubed, cc, all the same thing. So those were our derived units. And then we talked about measurements a bit, right? And when we talked about measurements, we talked about certainty or uncertainty in numbers. And if we're taking a measurement of something, so perhaps something, the red tape here, and this was in units of centimeters. This is 1 centimeter, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2 centimeters, 1, 2, 3, kind of something like that. We talked about what digit we have to include up to, right, whenever we take a measurement. And that's because there's always one digit that we have a slight uncertainty in it. And what did we call that digit? It was an uncertain digit, or it was the estimated digit, right? Because there's one digit whenever we take a measurement that we're estimating. So we always include up to the uncertain or estimated digit. All right, so if we have this measurement on a yardstick or a meter stick here, what would you guys estimate that measurement to be? And there's no one correct answer because the last digit's always going to be estimated. But at least two of your digits should be 100%, right? So you're measuring this red tape right here. What's going to be the first digit? 1, right? Because you know that this is calibrated, it's past 1 centimeter. So it's 100% past 1 centimeter. So your first digit is going to be 1 centimeter. Then it gets divided from there into fractions of a centimeter. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. Oops, I guess there should be an extra tick mark there. 1, 2, 3. Here, this is where I missed it. All right, there's an extra tick mark there. There's 9, right? So each one is 0.1 centimeters, what those little lines represent. On the ruler, those little lines exist there, which means that it's calibrated to be accurate to that decimal place, right? So this is calibrated to be accurate to the 10th of a centimeter. So that goes up to at least what? 9, right? Goes to 9. And you know for sure it's at least that amount because it goes past that tick mark. Then the last digit we have to include is which digit? The estimated digit, right? And that's the one that you're going to estimate there. And so what does that look like to you guys? Yeah, we'll say about 5, right? So 5 here is our estimated digit. So you guys had a little bit of practice doing that last time with the analytical scale, right? It's kind of a pain in the butt, but you had practice going all the way up to the third decimal place doing something like that. All right, so that was what we talked about when we talked about our measurement. It had to do with the precision of the instrument. All instruments have a little bit of uncertainty, and we include that estimated digit there. All right, any questions about any of that so far? Okay, and then last thing we talked about was significant figures. So I'll mention that briefly. Okay, template, I gotta go on, all right. Then we had the big portion of our lecture, which was the significant figures. All right, and so significant figures, non-zero digits, are those significant or not significant? Significant, right? These are significant. Anything that's not a zero is a significant digit. If we had sandwich zeros, right? This is zeros between two significant digits. What were those? Significant or non-significant? Those are significant, right? Significant. What about trailing zeros before decimal place? Non-significant, right? If we had trailing zeros before decimal place, they're not significant. So a number like 500, for example, those are not significant. And someone brought it up at the end of lab last time. Well, what if you have two significant digits, but you don't have a decimal place there? So like the number 10. How would you indicate that there's two significant digits in this number? So what you'll see if there is significant digits, if that zero is significant or not, is people will put a decimal place there, right? Or they will underline that last zero, and that indicates that it's a significant digit. And so this might pop up, for example, if you do a calculation and you know from your rules of significant figures that you have to have two significant figures in your answer, but it comes out to exactly 10, then you have to indicate that that's a significant digit. And so you'll see either the decimal place after or the zero will be underlined. What about trailing zeros after the decimal place? Yep, those are going to be significant, right? Anything after the decimal place are significant zeros. And then leading zeros, not significant, right? You can put as many zeros as you want in front of a number, it's still the same number. It doesn't change anything about the number. Not significant. So those are all the scenarios where we determine if a digit is significant or not. And then we also talked about operations with significant figures. We had multiplication and division, and then addition and subtraction. And for multiplication and division, what was the rule? Yeah, that's exactly right. So when you are multiplying two numbers, whichever one has the least number of significant figures, that's the one that determines the number of significant figures of your answer, right? The number with smallest significant figures is the number of significant figures of answer. All right, so if you had 3.0 times 2, 2 only has one sig fig, your answer has to have one sig fig. And we'll review that in a second in the actual example. And what about for addition and subtraction? What was the rule for that? That has to do with the precision of the number, right? How many decimal places does that number go to? So the answer is only as precise as your least precise number? All right, the answer is only as precise as your least precise number, right? And again, remember the way we did that is you line up the numbers according to their decimal place, and you draw a line to the right of the number with the least number of decimal places. And that tells you how many decimal places your answer has to go to, or what does the precision of your number have to be. So those were our rules for sig figs and what constituted a significant digit. All right. So we have this example. Am I good to move on to the next? Is anyone writing this? All right. You good, Julia? All right. So calculate the number of sig figs and calculate the answer that's going to be here in this problem. All right, so first step, determine the significant figures of each number first. Oops, sorry. So what rules are you going to use here? Right, we have addition and division combined, so that means it's going to follow the rules of addition and, not addition, sorry, multiplication and division combined. How many sig figs? Excuse me. How many sig figs does 3.15 have? 3 sig figs. How many sig figs is 1.53? 3 sig figs. And what about 0.78? 2 sig figs. So how many sig figs should our final answer have? 2 significant figures. All right, so if I do 1.53 times 3.15 divided by 0.78, I get 6.178, 8, and then a bunch of digits after that. I need 2 significant figures, which means I need the first 2. So do I just take 6.1 here? We have to round up, right? Because we're getting rid of digits, so we have to round in that case. And we round 1 to 2 because 7 is greater than 5, right? This digit 7 right here is greater than 5. So we round 1 to 2. So our final answer will be 6.2, and then whatever the units are if this was an actual physical problem. Any questions on that? Turn? You can do it in any order you want, right? So if you're, the nice thing about multiplication and division is that you can break this up into any 2 operations at the same time, and you'll get the same answer. Same?
So when it's 5, you round down, right?
When it's 5, you round up, right? So our rules for rounding, again. No, you're good. I forgot to mention it in the review. For rounding, right, if the rounding digit, which is the digit right before the cutoff, or right after the cutoff, the rounding digit is greater than or equal to, that's what that sign means, 5, we round up. If the rounding digit is less than 5, we keep it the same. Right? We don't change that number at all. Right, so this right here is our rounding digit. That's greater than or equal to 5, so we have to change this 1 into 2. That 2 gets added, plus 1. All right, any other questions on that? Okay. So we also have prefixes for all of our standardized units. So these prefixes basically move the magnitude of these numbers by a factor of 10. And so we can also put this in terms of scientific notation too, scientific notation. But you should be familiar, right, with seeing these prefixes and understanding what that means. Because you can add this prefix to any standardized unit and it changes the size of that number, right? So if we're talking about a second and we say, okay, well now I'm talking about a microsecond, that means that now I'm not talking about 1 standard second, it's 1/100,000 of a standardized second. Or 10 to the minus 6, right? Because if you're to move this over, 1, 2, 3, 4, 5, 6, to get back to 1 second. We move it to the right. So when you move it to the right, that means the exponent becomes negative, and we move it to the left, exponent becomes positive, right? So these prefixes here are shorthand for multiplying in moving decimal places, left and right, and multiplying or dividing by 10, which is the same thing, right? That's interchangeable. Are we multiplying or dividing by 10? And are we moving it to the right or moving it to the left? Right, so if we have mega as a prefix, usually that's a capital M as a symbol. This is like 10 to the 6 of whatever it is that we're looking at. So you can have a megameter, which is 10 to the 6 meters, or you can have a megagram, which is 10 to the 6 grams, or a megasecond, which is 10 to the 6 seconds, right? So these prefixes are just added in front of our SI units. Kilo, which you guys should be familiar with, kilogram, kilometer, that means 1,000. So that's 10 to the 3. Centi, like centimeter, is used mostly with meters, is where we see centi, but you can technically use it for any of the standardized units. That's 10 to the minus 2. Milli is like 1,000th of something. That's a lowercase m. That's 10 to the minus 3. And then micro is going to be 10 to the minus 6. And if we went even smaller, you start getting into the size, the range of atoms. All right, so I'm going to add one more column here. We can have nano, which is usually indicated by a lowercase n. That's going to be 0.000000001, and that's 10 to the minus 9. And a nanometer is about 10 times larger than an atom. Right, so you start to get really, really small sizes there. And again, these prefixes are just used to give us shorthand for having these exponents, right? So scientific notation is already shorthand for having to write this number a bunch of times. But let's say we didn't even want to include this exponent, but we know everything we're weighing is going to be about 1,000 grams or around that size. Then we say, okay, well, we're just going to measure things in kilograms now because that lets us deal with simpler numbers, right? I don't have to deal with 1,000 grams. I can deal with 1 kilogram instead. And this idea of, kind of simplifying numbers is a lot of what chemistry is about. When we talk about balancing chemical equations, or the idea of dealing with very large amounts of things, right? Because how many atoms of air are there in this room? An inconceivable amount of atoms, 10 to the 23 raised to, the 10th power. Okay, so these are ones you should be familiar with, right? So, for example, maybe the first quiz, if you guys are confused, you said, I don't remember what this prefix means. Can you write it on the board? I will. But after about the first quiz, and for the first exam, you'd probably be expected to see this and know what that means. Milli, okay, that means 1/1000th of whatever that unit is. Milligram, 1/1000th of a gram. Millimeter, 1/1000th of a meter. Okay. All right, any questions on that? I'll put a star because these are important. All right, so this next slide is kind of just illustrating what I was saying when we're moving stuff to the left or the right is the same thing as multiplying or dividing by 10. If we move stuff, if this is 1 unit, and we start moving stuff to the left, right, we're making a negative exponent. And so if we start with 1 gram, and we go to 1, 2, 3, we've gone from 1 gram to now a milligram. All right, the size of a milligram relative to a gram, 1/1000th. So again, these standardized units and the metric system is all just moving things to the left or right by 1 decimal place, which is multiplying or dividing by 10, right? And so if you ask yourself, how many centimeters are there going to be in a kilometer, right? If we start with, this is our 1 meter unit here, and we know a kilometer is 1,000 of those. We need to move it the same amount of decimal places until we reach centi, right? And so that's 1, 2, 3, 4, 5 places over, which means that we have effectively divided it by 10 to the 5. So that means there are going to be 10 to the 5 centimeters in 1 kilometer, or about 100,000 centimeters in a kilometer. And you don't have to do this method of moving everything by 1 decimal place if that doesn't resonate with you. You can also say, well, there's 100 centimeters in a meter, right? And then there's 1,000 meters in a kilometer, so 100 times 1,000 should give you 100,000, which is about 10 to the 5. And that kind of leads into, we can use these conversion factors and do unit conversions to go from 1 unit or 1 prefix of a unit to another unit, right? When we change the prefix, the effective unit has changed as well, right? A kilometer represents a different distance than a decimeter or decameter. And so what that math will eventually look like is if we have 1 kilometer, we know that per 1 kilometer, we'll have 1,000 meters, and per 1 meter, we have 100 centimeters. When we set up a calculation like this, things that are on the numerator will cancel out with things that are on the denominator. And what that means is these units of kilometer, numerator, denominator, kilometer cancels out. Meter and meter, those cancel out. So what are the only units that we're left with? Centimeters, right? So we cancel out the like units. We're only left with units of centimeters. And the number that we calculate is going to be 1,000 times 100, which would give you 100,000. And we'll go into more detail on what this is, but that's an idea of what a unit conversion is going to look like. So this equals 1,000 times 100 centimeters, which is 100,000 centimeters. Okay. Any questions on that? All right, so this leads us into unit conversions. So like I mentioned before many times, almost all problems in chemistry boil down to unit conversions, or what we say unit conversions, or dimensional analysis, right? Those can be used interchangeably, right? A unit is the same thing as a dimension for something. And so many problems in chemistry can be boiled down to just making sure you're getting to the right units. And so any unit can be converted into another unit with the appropriate conversion factor, and as long as they're measuring the same fundamental physical quantity, right? So you can't convert a length into a second, for example, but you can convert two types of length, like an inch into a centimeter. And so any conversion factor can be derived from a conversion equality, right? So if we have this equality here, we're saying 1 meter equals 100 centimeters, right? This is something you say verbally, it makes a lot of sense, but when you write it down as an equation, this is just what that you're saying in an equation form. From this conversion equality, we make two different conversion factors. We have one that says that for every 1 meter, there's 100 centimeters. And then there's also one other conversion factor. Does anyone have any idea what that might be? Just flip the other way around, right? So it'll be for every 100 centimeters, we have 1 meter per 1 meter. So we can write it as a ratio like this. Verbally, we say we have 1 meter for every 100 centimeters, 1 meter per 100 centimeters, and then vice versa, right? So for every conversion equality, we get two conversion factors. For every conversion equality, we have two conversion factors. And why might we need two conversion factors? Well, how do you know potentially which one you might need to use here? Yeah, I think you're on the right track. It depends where you want to go, right? If I want to go and cancel out meters, then maybe I'll use this one because I know meters is in the denominator, so it'll cancel out, and I'll be left with centimeters. If I want to cancel out centimeters, then maybe I use this one. So which conversion factor you use just depends on what you're converting between, right? If I want to go from centimeters, let's say I have 2 centimeters here, to meters, then I put 2 here times this, centimeters cancel out, I'm left over with meters. Let's say I have 2 meters and I want to convert that to centimeters, then I want the meters to cancel out, so I know that that should probably be in the denominator. All right, so the conversion factor, which conversion factor we use. Bless you. Is determined by what units or dimensions we want. So what are the two conversion factors between kilograms and pounds here? Yep, 1 kilogram per 2.20 pounds, or 2.20 pounds per 1 kilogram, right? And so if we wanted to find our answer in kilograms, we would use this conversion factor. If we wanted to find it in pounds, we would use the other conversion factor. And this is something you do a lot of intuitively. For example, if you're shopping and there's like a 3-for-1 deal, right, and you have a certain amount of money, you know, I get 3 for this amount of dollars, I have this many dollars, how many can I get? You're doing a conversion factor in your head generally, right? So it's something you do intuitively, but here we're just coming up with a kind of like a formulaic way of approaching these types of things. And the reason we do that is because usually when you're shopping and stuff, you're only doing one conversion factor at a time. But in chemistry and in natural sciences, usually you're converting from one unit to another system of units, and you might need 4 or 5 different conversion factors in between to get where you want to go. And so we can also have percentage unit factors, percentage conversion factors derived from a percent. So if we have 18% body fat by mass, then if, let's say, we're using units of grams or something, that means that we would have something like, for every 18 grams of body fat, we would have 100 grams of body weight. Right, so when we do this, we're treating the grams of body fat and the grams of body weight as two different units here. And when we're given a percentage like this, that's how that percentage gives us information there. Right, and we could use any SI units or any prefixes here as long as it represented a percentage, right? A percentage was when we did the whole, the part divided by the whole times 100. So here we know the part and we're dividing it by 100 to get a actual decimal place number instead of using a percentage, right? Because a percentage doesn't have any inherent units. And then we would also have another conversion factor for this. What would the other one be? 100 grams of body weight per 18 grams of body fat. So for example, if you knew this percentage for someone, and then you wanted to find what is their total body weight based off of if you knew how much grams of body fat they had, you would use this conversion factor to give you the total amount of body weight. Summer?
If you write that in the formula, what would it be?
So this one?
Yeah.
So if you were to write that, you would say that 18 grams of body fat equals 100 grams of body weight. So you could get a percent quantity, make a conversion equality, and from there you get two conversion factors. Which one you use depends on what units you want to end up with and what you're trying to solve for. Does that answer your question when you say like a formula equation?
I was thinking because I'm remembering something about an absolute value and times 100 and a true value, or am I off?
So if you're looking at percentages, if there's a chance that you might have a negative value, you use the absolute value for that. Sometimes when you're doing things where people are converting between units, there are shorthand notations. So if you go into nursing or dietary sciences too, people have like specific equations to use for like if you have this many pills in hand, what's the dosage that you use to calculate. In general, those will work for some of the problems, but it's kind of more useful to take a step back and kind of approach things this way, because those work if you're only converting between 2 units or something. But here you might need to convert between 5 different systems of units, right, in one calculation. So there isn't necessarily like an equation way to approach this. It's more, getting practice doing the problems and then applying this idea to each of them. Any other questions? Okay. All right, so let's look at this. How many milligrams are equal to 2.5 micrograms? Right? And so if we look at our prefixes, is a milligram smaller or larger than a gram? Smaller, right? A milligram means 1/1000th of a gram, which means that there's how many milligrams in 1 gram? 1,000 milligrams per 1 gram, right? So that means 1,000 milligrams equals 1 gram. We want to go to microgram, right? And so what I always find it useful in doing these types of calculations is you go from whatever unit or prefix you're looking at to the standardized one, so that's 1 gram here. to whatever unit you're going to do. So it's going to be two different conversions we do here. So 2.5 micrograms, and a microgram was smaller or larger than a gram. Smaller, right? And was it smaller or larger than a milligram? Smaller, right? A microgram was 100,000 micrograms are equal to 1 gram. So here we've set up two different conversion equalities, right? And each one of us gives us two what? Two ratios, right? Which is two conversion factors, right? So we should have 4 conversion factors here. So each one gives us 2 conversion factors. So we have 1,000 milligrams per 1 gram. And we also have 1 gram is 1,000 milligrams, and then the same thing here. Instead of writing this out, I'm just going to write 10 to the 5, or sorry, 10 to the 6. Should be 10 to the 6 micrograms per 1 gram is equal to, not equal to, but we also have 1 gram per 10 to the 6 micrograms. And sorry, this should be 1 million. 1, 2, 3, 4, 5, 6, 8. And so we have, whenever we have a unit conversion problem, the first step should always be to identify what our conversion equalities are, and then what our conversion factors are from those. So first we identify conversion equalities to get conversion factors. The next thing we're going to do is then determine where are we starting from and where do we want to end up. Right? So where are we starting from here? What unit and what number are we starting from? We're starting from micrograms, right? We know we're given this number, so we're starting from micrograms. And what do we want to find? We want to find milligrams, right? So we want to solve for milligrams. And so we can set up a little flow chart of how we're going to get from one unit to the other. So before even plugging anything in, we can say we're going to start from 2.5 micrograms. We don't have a conversion directly between micrograms and milligrams, right? We don't have that yet, or we don't have that on hand. So we might need to do an intermediate step in between. So what can we go to before we reach milligrams? Right. What do both of these conversion factors have in common? Grams, right? So we'll first go to grams. So we go to grams. And then from grams, we can go to milligrams, yeah. We can go to milligrams. All right, I know micro and milligram, they kind of look similar. This is the Greek letter mu, and m is just a lowercase m. So we're going to start from our micrograms, convert to grams, and then from grams we're going to go to milligrams. So let's see how we would do that. So we have 2.5 micrograms. I write it in parentheses here because that implies that we're doing multiplication. And we want to convert that to grams first. Right, so which conversion factor should we use, right? These are conversion factors between grams and micrograms. Which one should we use here? The left or the right? The right. So you guys said the right. So why would we use the right one here? Because that cancels out the units of micrograms, right? This is in the denominator, This is in the numerator, and we want the units of micrograms to cancel out. And so let's plug that in and see where that puts us. So we're gonna use this conversion factor. So we have 1 gram per 10 to the 6 micrograms. It cancels out the micrograms, and what units are we left with so far? Grams, right? But we don't want our final answer in grams. We want our final answer in milligrams, right? We want our final answer in milligrams because that's what the question is asking for us. So now we know we have a conversion factor between grams and milligrams. So which one are we going to use, the left or the right here? We should use the left, and so why would we use the left?
We're trying to find the milligram.
Because we want the milligrams, and we know we have units of grams in the numerator here. So if we use this conversion factor, multiplying it by this, we know the units of grams are going to cancel out with each other, and we'll be left with milligrams. So we use 1,000 milligrams per 1 gram. The grams cancel out, and all we're left with is milligrams, which is what we want. And so you guys could then plug this into your calculator, and you'll get that you have 2.5 times 10 to the minus 3 milligrams. In general, for conversions between standard units like this, you don't consider the significant figures in each of these. So we start with 2 sig figs and we end with 2 sig figs. Vanessa?
How do you get the 10 to the 3?
Because if you plug this into your calculator, it'll be like 10 to the 3 over 10 to the 6, which is like 10 to the 3 minus 6, which is 10 to the minus 3. I just did it. If you plug it into your calculator, you should probably get 0.0025, which is like 2.5 times 10 to the 3 in scientific notation. 10 to the minus 3, sorry. Another way of doing this is when you're dealing with powers of 10. If you have 10 to the 3 over 10 to the 6, right, which is 10 to the 6, 1,000 is 1, 2, 3, 10 to the 3. This is equal to 10 to the 3 minus 6. 3 minus 6 is equal to negative 3. Right, it's a lot easier. I can just write this as 10 to the 3 as well. And so what we're doing with these conversion factors is what I'm plugging into the calculator effectively is all of these in one expression, and then doing that calculation. So this is like 2.5 times 1 times 1,000, all divided by 10 to the 6 times 1. I'll write that on the next page just so you guys see what I'm actually saying when I say that. So in the calculator, it's like 2.5 micrograms times 1 gram times 1,000 milligrams all over 10 to the 6 micrograms times 1 gram. So this looks more like the problems that we already did when we're plugging this into our calculator. The reason I write it out sequentially, like I did as ratio times ratio times ratio, is because sometimes it's easier to see how the units are canceling out when we do it sequentially like that. Because you can do each step and say, okay, what do I multiply by this to cancel out the units I want to cancel out? Versus here, if you were writing this all as one gigantic fraction, it'd be kind of hard. How do I plug in a conversion factor into here? When we do it this way, this is the same expression, I just moved the parentheses here. We can say, okay, well, I start here. This is my first step. I know I want these units to cancel out, so I'm going to multiply this conversion factor. That's my second step. Does that make sense? All right, so let's take like a 5-minute break. We'll come back. We'll continue with conversion factors. And so we'll do some with actually, some dosage examples. This one? Okay. All right, so let's now look at a different problem. So this is going to be a little bit more challenging, right? It's not as straightforward what our conversion factors and inequalities are going to be. So we have a doctor orders 0.5 grams of chloromyidin to be given to a patient, and it comes in 250 milligram tablets. How many tablets should be given to the patient? Right, so you want to give them 0.50 grams of chloromyidin. And you know that it comes in per tablet 250 milligrams. So how many tablets do we need to give them, right? So we need to identify where are we going to start from and where are we ending, and then all of our conversion factors, right? So does anyone know how we can get a conversion equality from this problem? Right? Ultimately, what are we trying to find? The number of tablets, right? And we're given that the doctor is giving the dose in what units? Grams, right? So we're going from mass to tablets, right? So we're probably going to have to use a couple different conversion factors here. We need one to go from 1 unit of mass to another unit of mass, which is grams to milligrams here. And then we're going to need another one to go from milligrams to our final unit of what? Tablets, right? So see if you guys can look at this and determine your 2 conversion equalities that you're going to use here, and then get your 4 conversion factors from that. What's our conversion equality for going between grams and milligrams? 1,000 milligrams equals 1 gram. And our 2 conversion factors, 1,000 milligrams per what? 1 gram. And then what's the other one? 1 gram per 1,000 milligrams. All right, so that's 1 conversion factor. What about the other one? It's going between what 2 units? Milligrams and tablets, right? So what's the equality we have there? 1 tablet equals how many milligrams? 250 milligrams, right? So 1 tablet equals 250 milligrams. And so our 2 conversion factors should be what? 1 tablet per 250 milligrams and 250 milligrams per 1 tablet. All right, so we have our 4 conversion factors that we need for this problem now. We're not going to use every single one of them, but we know we see them in front of us, so we can decide which ones we need to choose. And we know we want to start from where? We're going to start from grams. And what's the actual number of grams? 0.5 grams, right? 0.5 grams. And we want to end with what? Tablets. All right, so see if you can come up with a flow chart for how you'll get between these 2. And then if you can, determine which conversion factors you'll use to kind of make that journey. Unit we're going to in between grams and tablets is what? Milligrams, right? We're first going to go to milligrams, and then we're going to go to tablets. And we know we're starting from 0.5 grams. And I'm going to write that just to emphasize that this is in the numerator. It's over 1. Anything that's just a number is technically over 1. To get to milligrams, what conversion factor am I going to use? We can use 1,000 milligrams per 1 gram, right? And how do you know you want to use that one? Yeah, you want the grams to cancel out, right? We have grams in the numerator, we need grams in the denominator, and that'll leave us with units of milligrams. So we're going to use this conversion factor, 1,000 milligrams per 1 gram. Grams cancel out. What we're left with units in milligrams. And the last step is going from milligrams to tablets. And our conversion equality here is 1 tablet equals 250 milligrams. And these are 2 conversion factors. So which one are we going to use there? The left or the right? The left, right? And so why do you want to use the left? We want milligrams to cancel out. Milligrams in the denominator for this conversion factor. Milligrams in the numerator here, so those will cancel out. We'll be left with units of tablets. So we're going to use this 1 tablet equals 250 milligrams. And so this, the numbers that we put in our calculator, is going to be 0.5 times 1,000 times 1 divided by 1 times 250. And this is all in units of what? What's left over? Tablets, right? Or we don't plug units into our calculator. That doesn't allow us to type that. So those are just the numbers that we're plugging in. So we plug it in, 0.5 times 1,000 divided by 250. We should get, this is all equal to 2 tablets. So 2 tablets is what we should get for the patient. And
How do you get the in the calculator?
Oh, in the calculator, so all I did for in the calculator is I just combined everything that's in the numerator into one expression, and then everything that's in the denominator there. Right, so I know, so because sometimes it can be confusing when we go from like multiplying these ratios. You can multiply, this times 100 divided by 1 times 1 divided by 250 if you want. That works as well. It's just sometimes people prefer to put it all in the calculator in one expression.
I put it in the first way and it gave me the same answer.
Yeah, either way, the reason that it works is because it doesn't matter which order you do things. So you guys might remember PEMDAS, right? And multiplication has the property of commutivity, which means you can move it around, right? All I did here was I got rid of these parentheses and just put them all the way on the outside there, and that gives you the same thing. I could multiply this times that, and then divide it by 250, then multiply it by 1, divide it by 1, any order, and you'll get the same answer no matter what. It's a nice thing about multiplication and division. Any question? Okay, so I know that this, you might be able to look at this question and say, okay, well, I know just off the top of my head that I should get something like that. Here, since it is in 250 milligram tablets, that can make things like, okay, I actually do have to work this through and put it in a calculator. But technically 250 milligrams is like 0.25 grams, and that's half of 0.5, so you need 2 to account for that. Okay, any questions on that? All right, so let's look at this one here. The order is to give a patient 250 milligrams, so another milligram, another dosage. The bottle's direction is to add 9.5 milliliters of sterile water to the vial to yield 0.5 grams per milliliter. Right? How many milliliters should be given to the patient to fill this order? Right, so take a second to think about where we're starting from, where do we need to go, what are our conversion equalities, and therefore our conversion factors. And for our conversion factors then, which ones do we use to go from one set of units to the other? And think. So for this one, when I look at this, it might be easier to start from thinking about where we're starting from and where do we need to end up with, right? So we starting from what? What is the units that we're starting from? Milligrams, right? Because we want to give a patient a certain number of milligrams, right? So we know how many milligrams we need to give that patient. So we're starting from 250 milligrams, and we want to end with milliliters. right? And so we need to go from milligrams to milliliters. And what other unit conversion are we given in the problem? Grams per milliliter, right? We're given a grams per milliliter, and we're actually given this quantity right here is grams, 0.5 grams per 1 milliliter, right? Whenever you see a unit that's in per like that, that's the same thing as writing 0.5 grams per 1 milliliter, right? And so is that a conversion equality or a conversion factor? It's a factor, right? Which means that we can get a conversion equality. We don't necessarily need to get a conversion equality. Usually we get the equalities first to get the factors, but this gives us a factor. And from this factor, we also get another factor, right? What's the other factor? Yeah, it's the inverse, right? The same way when we get it from our conversion equality, we get it both ways. So this also gives us a conversion factor, 1 milliliter per 0.5 grams. Which one we use, we don't know yet, right? And so what's one other thing that we notice from here? We want to end with milliliters. We're given a conversion between milliliters and grams, but we're starting with milligrams. So we also need to convert between what two things? Yeah, we need to go from milligrams to grams. We can't use those conversion factors unless we're in units of grams first, right? So we also need to go from milligrams to grams. And how many milligrams are in 1 gram? 1,000 equals 1 gram. We get our two conversion factors that we've seen before, 1,000 milligrams over 1 gram, and then 1 gram over 1,000 milligrams. And so now we have all the conversion factors we might need. Is there anything in this problem that we're also given? We're given 9.5 milliliters of sterile water to the vial to yield a concentration or the amount that's in this solution, right? Is that relevant at all here? We don't need to use that at all, right? That's just saying that that's how you prepare the bottle. But once you prepare the bottle, that's what you're actually going to be using to give a certain dosage to the patient, right? So this is information that we don't need. So that's just extraneous information. That's just kind of a number that's put in there to throw you off. I'm not a big fan of giving numbers to throw you off, but if you're taking any standardized test, if you want to take the MCAT in the future, they will do stuff like that. Okay, so now let's come up with a way we're going to go between these. So we have our 4 conversion factors. We start with milligrams, and what's the first thing we're going to convert to? First, that's going to go to grams. And then from grams, we can go to milliliters. How do we know we're going between these units? Well, this is our conversion from milligrams to grams that we get here. And we know that we want to go from grams to milliliters because that's what our other conversion factor gives us. All right, so see if you can set up and solve for the amount of milliliters you need to deliver this amount of medicine to the patient. We start with 250 milligrams over 1. We multiply it by the left or right conversion factor between grams and milligrams. The right, why? Because we want units of what to cancel out? Milligrams. And then what's the second conversion factor we use, the left or the right up there? Yep, it should be on the right because we want units of grams to cancel out. We want to be left with milliliters, right? 1 milliliter and 0.5 grams. So grams cancel out. And we're left with just units of milliliters, which is what we want. So in your calculator, if you're inclined, you can plug in 250 times 1 divided by 1 times 1,000 times 0.5. And all of this is in units of milliliters. And that should give you 0.5 milliliters. And given the sig figs here, these don't count towards sig figs because they're going between different prefixes for standardized units. 250 has how many sig figs? 3? Or no, this one should have only 2, right? Because this is a trailing 0 before a decimal place. So we have 2. And then 0.5 has how many sig figs? 1. So our final answer should have 1 sig fig as well. When you're given a question like this on a quiz or an exam, like I will tell you which ones to consider for the sig figs, right? So generally you don't consider things like constants and standard conversion factors between the prefixes. But I'll make it clear in the problem when you guys are being asked on a quiz or an exam. Okay, any questions on that? All right, so we're gonna move ahead a little bit. There's a couple other problems on doing unit conversions in general with like dosages and things like that, Sam?
So for conversions, we don't need to worry about significant figures.
So you do worry about significant figures, but there's certain things that in general in practice you don't actually consider. So for example, in this problem, it didn't give you that 1,000 milligrams is equal to 1 gram. That's something you're expected to know. So these numbers are not considered in significant figure calculations. Or if you're given a constant value, like when we get to the ideal gas law, the ideal gas constant, you don't consider that in significant figure calculations of your calculations. And as we see more physical problems, we'll get examples of that. All right, so before we end for the day, I'm going to introduce density. All right, so density is a mass per unit volume of a material. It's a physical property of the material. Right, so that's something inherent to it. What it has to do with is how close are the atoms packed together in whatever that material is. The units are usually grams per centimeter cubed, or grams per milliliter is how you see it in most texts. You'll see it that way, but it can be any mass per unit volume. The density can be expressed in those units. And so this is going to be a derived unit. Because it's a combination of SI units. And so we talked about that before. And so here we have an example of 3 different materials that all have the same volume. How do you know they all have the same volume? Well, they all occupy the same 3D space here, but they all have different masses. That's because the density for each of these are different. We also have the same materials here. Now they all have the same mass, but we see that the volume has increased, right? So density gives us a relationship between the mass and the volume of a material. And the equation for density is that the density is equal to the mass divided by the volume. The M is the mass, capital V is the volume. And so for a given density, right, if we want objects that have different density to have the same mass, they need to have differing volumes, right? So that's what this illustrates right here, right? If you have, half a pound of steel versus half a pound of water, you're gonna need a lot different amounts of either of those to have the same mass. And if you want them to have the same volume, then they're gonna weigh differently, right? So now if you have, you know, a water bottle filled with water versus a water bottle filled with iron filings, they're gonna weigh differently than each other. So density gives us a relationship between these. Density also gives us a conversion between grams or mass, between mass and volume. Right, so because it's a ratio of the mass over the volume, the density value, that also gives us a conversion factor of the volume over the mass as well. And so what I mean by that is, example, if we have a density is equal to 0.5 grams per milliliter, then that's two conversion factors, 0.5 grams, whatever the substance is, per 1 milliliter. And we also have 1 milliliter per 0.5 grams of that substance. So we can use the density as a conversion between things. So if we weigh an unknown volume, but we know the density of it, we can use that to calculate whatever the mass of the material is, or the volume of the material is. Okay, and we'll finish up talking about density next time, and then we'll start talking about the classifications of matter. So we didn't get through that today, so I'll extend the problem set till next Tuesday, just so we can make sure we cover all of it before it's due. And then again, we have our quiz a week